In this video, we're going to be talking about the Pearson's product moment correlation coefficient. In order to be able to talk about this, we first need to talk about what type of data we are now going to be studying. So we're moving away from a one variable statistics and we're going into two variable statistics. And this type of data is called bivariate statistic, bi meaning two, and then variate for our variables. So we're now going to be studying two different variables, and our task is going to be to model the best fit for this data, and we're going to be measuring how the relationship is strong or weak between these two variables. So this is what we're trying to do through this video. First, let's think about this situation. So I have some data here. I'm told at a junior tournament, some young athletes each throw a discus. The age and distance thrown are recorded for each athlete. So we see athlete A all the way to L, the age of the athlete, and the distance. Do you think the distance an athlete can throw is related to their age? Okay, well, this question, it's pretty hard to answer if we just look at the data. This is not an appropriate representation for us to see if the distance and the age is actually related. So what you probably would do at this stage is to do a scatter plot. So you would probably do a little graph like this where you have each of your points represented. And now we can answer the question a little bit better. Do you think distance of an athlete can throw is related to the person's age? Well, as we see on the graph, it seems to be a general trend that as the age increases, the distance increases. So we probably answer this first question, yes, we think there is a certain, as the age increases, the distance does increase. What happens to the distance thrown as the age of the athlete increases? I kind of answered this one already. There seems to be a general trend where both are increasing together. We're going to skip to question D. How can we measure the relationship between these variables? Now, this is going to be our focus for today. How do we measure this general trend? Okay, we seem to see they're increasing, but how do we measure this increase? So that's going to be our objective for today. We're going to be talking about this correlation. So correlation refers to the relationship between our two variables. Now our variables will always be numerical. There's always going to be some numbers. So we're going to talk about this relationship, this correlation between them. There's several specific characteristics that are really important for us to consider. The first one is our direction. Positive, negative, or no correlation. So we're going to talk about what it means to have a positive correlation when we're increasing together and a negative correlation when we're decreasing together. We're going to talk about the strength of the correlation. Is it a perfect correlation or is it moderate correlation? We're going to talk about linearity. So these are looking at the types of trends. So in this video, we're going to focus only on a straight line trend, so a linear trend, but there are different types of correlation. And of course, outliers are important to notice. It's isolated points that don't follow the trend. So these outliers make our correlation very sensitive to them. And the last part, which is probably the most important part, is correlation does not equal causation. What do I mean by this? When we find that two variables are correlated, there is a relationship between them, well, that does not mean that one causes the other to happen. So the causation is something that can only be shown through different tests. So it can only be shown if you push this a little bit further. Normally, this is not a mathematical analysis. It would be something like a psychological analysis for causation. So here we have a little representation of our outliers. So if we have our line of best fit, which we're going to talk about in a few minutes, and we have a point which doesn't follow the general trend, then we're going to call this one an outlier. Okay, so today's focus, like I mentioned, is going to be on one specific type of correlation, which is called the Pearson's product moment correlation coefficient. I'm going to simplify this to just Pearson for simplicity's sake. What's important to realize is that we can only use the Pearson's correlation if we have linear data. So only a linear correlation for this one. How do we measure the strength of a linear correlation? Well, we're going to be using our calculators, okay? So we're going to be using our calculators, we're going to put in all of our data, and we're going to run what's called a linear regression. But if you want to know what the calculator is doing, this is the formal definition for the value that they're going to give us, which is called the Pearson's product moment correlation coefficient. And this value R is going to tell us the strength of the correlation between our two variables. Now, you do not need to know this formula. We will never use this formula in the course, but it could be useful for your potential IAs. The calculator is going to give us a coefficient, which we call the R value. And this number is going to be between -1 and 1. What does it mean? Well, we're first going to talk about the sign. If you have a positive value, then we're looking at an increasing correlation. If you have a negative, then we're looking at a decreasing correlation. And if the R value is 0, well, there is absolutely no correlation between your two variables. The next thing we talk about is the size of the relationship. Now, the closer we get to 1 or -1, the stronger our correlation is going to be. So we normally say that if we have something between 0.75 and 1, or -1 and -0.75, we're at a very strong correlation. And that's our objective. We would like to have a strong correlation because that's going to allow us to then pursue with this problem. Okay, now it's time to get your calculators out. So pause the video, go get your calculator. Our first example is the botanical gardens have been trying a new chemical to control the number of beetles infesting their plants. The result of one of their tests are shown in the table. So we have 5 samples. We have the quantity of chemicals used and the number of surviving beetles. We're asked to draw a scatter diagram. Please always use your calculator to do this. Determine the correlation coefficient R, and to describe the correlation between the quantity of chemicals and the number of surviving beetles. So the first thing we're going to be doing is in your calculator, we're going to be going and putting our variables into our stats. So we're going to edit our list and we are going to clear whatever data we have. So we're going up, clear, enter, and then to the next list, clear, enter. Now we're ready to put our data in. We're going to put our two variables in separate columns. So L1 is going to be my quantity of chemicals, and L2 is going to be the number of surviving beetles. Pause the video and input your data. Once you've inputted your data, always make sure that they align with each other. There should be the same amount of data points in both columns. Now, we're going to draw a scatter diagram. In order to draw a scatter diagram, we're going to have a few steps that we need to do. Now, your calculator is always programmed so that when you click on the graph option, it's going to give you a graph of whatever functions you've inputted to your calculator. Well, we don't want to input a function, we want to input our data set. So instead of putting in a y value for a graph, we need to tell our graph, actually, I don't want you to put a function, I want you to put the data points. So you're going to go on to second, click on the y is equal to, and this is going to bring you to your stats plot. Now, notice that what we want is we want our first stats plot to be on. So you're going to click enter. You're going to go on is what we want. Type, yep, we have many different types of representations we could use for our data, but we're going to want the scatter plot for the first one. Our X list, so our X list being our quantity of chemicals, is in L1. Our Y list is in L2. Okay, here you have a choice of points. It doesn't matter what type of point you want to use. I like to use these big squares. You can use a plus, a little dot, or a really, really small dot. It's completely up to you, and have fun changing the colors as well if you want that. Now, once this is set, we have told our calculator, okay, my plot is on, therefore, on my graph, I should see my data points. Now, why do I don't see any data points right now? That's because my window is probably not set to what I wanted. So the window is talking about our domain and our range that we see on our calculators. So we're going to go click on window. Right now, my window for the x values goes from -10 to 50. That's way too big for me because if you look at my x values, I'm going from 2 to 9. So a good domain for the x values, we always go a little bit under and a little bit above the minimum and maximum. So if 2 is my minimum, then I might want to change this to 0. And then if 9 is my maximum, I might want to change my x maximum to 10. The scale means how many are we increasing each time. We can keep that to 1. Now we're going to do the same thing for our y values. Right now my y values minimum is at 1,000 and 4,000 maximum. So that just means that the question I was doing before, I needed these types of data. Right now I see that the smallest y value I have is 3 and the highest y value I have is 11. So maybe a more appropriate representation would be from 0 to 15. Once we have a window that's appropriate, we're going to go back on the graph. And now we see all of our data points. So our 5 data points are here. So we're good with A, drawing the scatter diagram. This is what it looks like. B, determine the correlation coefficient. Okay, the correlation coefficient, in order to do that, we need to run what's called a linear regression because we're looking at a linear regression here. How we're going to do that? We're going to go back on stats. We're going to calculate. Now, in the previous videos, we only had one variable, so we would do the first choice. But now we want to do a linear regression. So this is what we're going to get. Linear regression is our 4th option. We're going to tell our calculator that our x is in the L1, our y is in the L2. We don't have any frequency, and we are ready to calculate. Now, if your calculator looks like mine, where you only have A and B, which represents the values we're going to need for the line of best fit, we're missing something. We're actually missing the R value. Where is the R value? It should pop up on this screen. If this is your case, then that just means your calculator is not in the proper mode. So if you don't see a R value, you're going to go on mode, and you're going to scroll down to where you see stats diagnostic. So this one here. You want to move your cursor from off to on and click on enter. And now you'll be okay to get all of your data. So we're going to go back and do the same steps. Stats, calculate, linear regression. We have L1 and L2, calculate. And now we see the most important values, which is our R value. So the R value, negative 0.859, we can round to 3 significant figures. So our value is going to be negative 0.859 if we round it correctly. So that's our B. Describe the correlation between the quantity of chemicals and the number of surviving beetles. Well, the first thing that we can say about this correlation is that we have, in fact, a negative correlation because of the negative sign. So this means that our correlation is decreasing. Another thing that we can say, so here we talked first about the sign. The second information is about the strength. So negative 0.859, well, this falls into our strong category because it's between -1 and negative 0.75. Strong. There we go. So this is how we're going to describe our data. So just a reminder, if you didn't see the R value, make sure you change your mode for the diagnostic. Now, the next part of looking at the linear regression is that if we do find a R value, a correlation coefficient, which is strong, then we can go and draw the line of best fit. What is the line of best fit? Well, it's an equation that most accurately describes our data points. So it describes the trend that they're going. It's going to be a straight line because we're doing Pearson, which is a linear correlation. And we're going to call it the regression line, which is y on x. And it's going to have this equation here, y is equal to ax plus b. So now already we're making a link from our previous example where our calculator gave us information about a and b and r. So a and b, a is the slope of our straight line and b is the y-intercept of our straight line. The r squared value for this linear regression is not important at all. So you can kind of forget about the r squared value. We're not going to be using it. What's interesting about this line of best fit is that the mean point, which is the mean of x and the mean of y, is always going to be a point on our line of best fit. Now, this is how you get the line of best fit with your calculator, right? So by running the full linear regression, it's going to give you the equation of a line. And then with this line, we are going to be making estimations. The two types of estimations we can be making, interpolation and extrapolation. So when we're doing interpolation, that means that we're guessing some values that are within the data range that we have. If we're doing an extrapolation, then we're guessing values that are outside of the data range that we have. And we're going to do an example to make sure we understand what's the difference between these two. So our first example, on a hot day, 6 cars were left in the sun in the car park. The length of time each car was left in the sun was recorded, as well as the temperature inside the car at the end of this period. Calculate the x bar, so the mean of x and the mean of y. Draw the scatter diagram, find the equation of the line of best fit, predict the temperature of the car which has been left in the sun for 35, predict how long it will take for the car to reach 55, and comment on the reliability of our predictions. So first we're going to go ahead and input our data in our calculator, so pause the video and input the data. Once your data is inputted, then our first question was to calculate the mean for both x and y. Now we want to do this separately. We want to have the mean for x and the mean for y. So we're going to do, same as we've done in previous videos, we're going to calculate one variable statistics and we're going to go and do them separately. So if L1, that's going to be my x, I'm going to calculate and I'm going to get that the mean of my x is 30. So let me write this down here. The mean of my x is 30. Next, I'm going to do that for my y. So stats, calculation, one variable. Instead of having L1, I want to put L2, so second function 2. And I'm going to calculate, and the mean of my y, even though it's written x here, remember we put our values for y, so the mean for my y is going to be 38. So that's the first question here. Next, they're asking us to draw a scatter diagram for our data. So we know how to do that now. For the scatter diagram, I'm going to go second function y is equal to. Make sure that my plot is on. So you see it's on here, so we're good to go. Let's go on the graph and see what we have. Again, we don't see anything because our window is not appropriate to our data points. So we're going to go and change our window. Let's look at our x values. Our x values, my smallest x seems to be 5, and my biggest x seems to be 50. So 0 is appropriate for the minimum, but I need to make the maximum something bigger than 50, so let's say 60. Next, let's look at our y values. Smallest value seems to be 28, so maybe I'm going to want to use 20 for my minimum. And my biggest value seems to be 47, so maybe I want to use 50 here. And I'm going to go back on my graph. Now I see my data point. So this is the scatter plot. Now what I want to do is to draw a line of best fit for this data point. So we're going to go and find the equation for our line of best fit. We go in statistics, calculation, fourth option, linear regression. Our x values are in L1, our y values are in L2, and we are ready to calculate. Now we have A and B, our slope, our y-intercept. So we're able to answer question C here. Also, let's notice the R value. I know they don't ask us in this question what the R value is, but we have an R value of 0.973. This is huge number. It's super close to 1. So we have an almost perfect correlation here. Very, very strong correlation. Predict the temperature of the car which has been left in the sun for 35 minutes. So 35 minutes, this is an information about our X value. Okay, so we're going to be replacing X by 35, and we're going to be seeing what is the temperature that we're expecting it to be. So in your calculator, you can go second function quit, and you're replacing X by 35. And we're expecting to have a temperature which is going to be 39.8 is going to be the expected temperature we have when we have our time being 35. Next question. Predict how long it will take for the car temperature to reach 55 degrees. 55 degrees, this is the value for y that we have. So this time we're looking for x. So if we're looking for x, then we need to replace y by 55. And we are going to have 55 is equal to 0.366 times x, and then plus 27. And we're going to get a value for x, which is 76.5. Okay, now let's talk about F, which is the last part of this example. Comment on the reliability of your prediction. For the reliability, you need two things. You need to have a strong R value, and it needs to be an interpolation. So let's talk about D first. The temperature when we have 35 minutes. 35 minutes, let's see. Is this an interpolation or extrapolation? If we look at our x values, whoops, our x values 35, yep, it's in the range between 5 and 50. So this would mean that we are doing an interpolation. And as we saw for our statistics, we do in fact have a really strong R value, right? We said the R value is 0.973. So we have strong correlation and interpolation. So we would say that D is a reliable prediction. For E, we still have a really strong R value, right? The R value hasn't changed, but let's talk about the X value. Our X value we found is 76.5. That's way above our maximum data point, which is 50. So in this case, for E, we would be doing an extrapolation. So we would say that E is not reliable, even though we do have a strong R value. So I hope this helped to understand our key takeaways for this presentation. So linear correlation, we're talking about the R value. So this is telling us the sign and the strength of our correlation between the two values. And we talked about finding the line of best fit. We only are using the line of best fit when we do have a strong correlation. And then we talked about making estimates, so the interpolation versus extrapolation when we have a strong R value and we're doing some estimations.